Today, I would like to show you quite a lot of different examples of how surface analysis can help engineers, material developers, industry innovators in the work that they are doing. And I will start with the story. So several years ago, the manufacturer of semiconductor sensors faced a nightmare scenario. They released new sensors that were critical components in car industry and airline industry. And then the customers started reporting failure in the field. That cost millions of dollars. Protective coating started to peel away in the field, and that created millions of recalls and downtime. Of course, the general process is to check all of the components, all of the stage of the process, and nothing seemed to show any obvious defects. So they turned into surface analysis. So XPS detected invisible contamination layer. Auger showed that it's not just present in homogeneous, but it's present in streaks. And TOF-SIMS really pinpointed what it was. It was a siloxane residue from cleaning solvent. So adhesion was destroyed by the solvent. So the power of surface analysis is not just providing an answer, but actually saving from millions of dollars in making mistakes. So the cleaning process was corrected, the adhesion was restored, and costly recalls were avoided. So why surfaces are so critical? Well, they are everywhere. They where corrosion is happening, the adhesion take place, like in the example, it's a fictional example that I just showed. Catalysis happens on interfaces of the catalysis particles. Mechanical particles are being lubricated at the surface when the particles are in contact. Medical devices that are implanted in body, they have an interface with the body. Electrical contact is made at the surface. The rubber meets the road, so the tribology happens on the surface. Thin layer forms, whether it's a multi-layer thin films or paints. Semiconductor operates or phones have multiple surfaces and interfaces, solar panels and batteries. So everywhere you see there are surfaces. So today I hope that I will show how we can actually help analyze surface and relate it to the performance, to the property of the interest. So when we speak about the surface, what does that physically mean? There are a number of atomic layers that actually define different types of properties. For example, you can see that the very top layer affects wettability, catalysis, electronic properties such as work function, optical properties. Much larger number of layers can define the whole thin film structure. So you can imagine multi-layer thin film structures that are much thicker than one atomic layer, and the properties and performance of those devices will be defined by more of atomic layer. And there are some properties in between: corrosion, passivation, oxidation, diffusion. So when you are thinking of the property that you are interested in making better, you need to analyze, really understand what a physical dimension that are responsible for those properties. So how do we analyze surfaces? So in any analytical technique, you need to have a beam or a probe that will create some disturbance on the sample, on your interest material. And you can create disturbance and you create a signal or beam out. So if you think about what particles can be used to create disturbance and to be ejected, photons, electrons, ions are most commonly used. So all particles have different penetration depths, or the distance that they travel within the medium before they lose energy completely. So photons travel on the order of microns, while electrons and ions only travel 1 to 2 nanometer. So therefore, in order for us to design a surface analytical method, we need to use either electron or ion, either as a probe or as a signal. And there are analytical techniques that have combination of all of these particles as a probe or signal. And today we're going to review several of them. So this is the phi analytical technique portfolio. So on the left side, we have a diagram that shows HuxPEX, XPS, Auger, and TOF-SIMS in relationship in relative analysis area and information depths. So where is the depth from which we obtain the signal? So let's start with Auger. So Auger, as you can see, we are using electron in and electron out. So both very surface sensitive probes. So the sampling depth is very similar to XPS on the order of 1 to 10 nanometers. Let's see that highlighted in blue, something that's really unique about Auger from this set of techniques is very high lateral resolution. In XPS and HOXPS, which HOXPS is a high energy XPS, we are using X-rays as a probe, and X-rays, as we've talked before, they penetrate quite deep up to micron, but we're using electrons as our beam out. So that would provide surface sensitivity of our technique. XPS is very similar in sampling depths to Auger, but with higher X-ray sources in HOXPS, we can increase that depending on the energy of your X-ray. So in the case of the instruments that Phi has, we have a chromium source, the sampling depth is on an order of 3 to 30 nanometers. And you see several things that are really highlighted that are really unique about XPS and HOXPS, the chemical information and excellent quantification. And the third technique or instrument is TOF-SIMS. In this case, we are using ions as both probe and analysis. It has better spatial resolution than XPS, but a little bit worse than Auger. But it's the most surface sensitive. So we can see that ions are coming from the 1 to 2 nanometers. And something that is highlighted here, the unique feature of TOF-SIMS is high detection limits. So we can detect contaminants and dopants at parts per million. And it provides unique structural molecular information. So this graph is familiar for everybody. So this is a really famous graph from EEG that has a detection range on y-axis and spatial resolution or analytical area on the x-axis. And I highlighted where the three analytical techniques that we're discussing today fall onto this graph. So we can see that both Auger and XPS are not the techniques that have high detection limit. Auger has really good spatial resolution. Well, TOF-SIMS is in the quadrant where everybody would like to be. Everybody would like to be to detect as small quantities as possible from as small area as possible. So TOF-SIMS has a really excellent both spatial resolution and detection limits. So this is the three instruments that I will be presenting data today from that are in portfolio of Phi. We have Phi NanoTOF-3, which is time-of-flight mass spectrometer. We have Phi Genesis, that is our XPS system. And with hard X-ray, we still have HOXPS as an option. We also have Auger option, which we'll be showing some examples of that today as well. And of course, we have a standalone Phi 710 Auger electron spectrometer. So why XPS and HOXPS? So XPS is the most widely used surface analytical techniques because it can be applied to the most broad range of materials. Everything that is vacuum compatible can be analyzed in XPS instrument, and it provides valuable quantitative and chemical state information. That's why XPS became a routine technique in any materials paper that you can find right now. XPS is always present. With HOXPS, with high energy source, we can also probe deeper into the sampling depths. Phi XPS instruments are de facto imaging XPS instrument. They allow us ability to provide spectra and maps from lateral resolution as small as 5 microns for aluminum X-ray source and 15 microns for the chromium X-ray source. So you can see here that we can create, by scanning X-ray, we can create secondary electron images that allow us really nicely to look at topographical and chemical heterogeneities and identify areas for analysis with 100% certainty. And we can then collect maps from areas of interest. A chemical map of fluorine is shown here. So how does it work in XPS? So we have an electron gun, and this is microfocus gun. So the electron gun is creating a pattern on the anode surface. And it creates X-rays. The X-rays goes through the monochromator, and then the same pattern is being bombarded onto the sample, and that causes ejections of electrons. The electrons are going through the analyzer, and we count them. The intensity of how many electrons are tells us how much of this element present, while the position of the peak or the binding energy in the spectrum tells us what it is. And not only what element it is, but also what is the chemical environment of this. TOF-SIMS is the second technique. So why we care about TOF-SIMS? So TOF-SIMS is a key analytical techniques for detecting, identifying, and imaging distribution of elements and molecules. It's the technique that allows us to get 50 nanometer spatial resolution with full math range. So we can detect, we have really excellent spatial resolution in imaging mode, and we have excellent molecular information, so we can really separate different fragments in a spatial relationship. And we also have parallel imaging platform that allows us to really analyze fragmentation and confirm identification with really high accuracy, and allows analysis of really most challenging samples, rough samples, etc. So how does TOF-SIMS work? So we have a primary ion source that is, there are different sources that are used to defragment the surface of the sample, and we create ions, and these ions are directed through the Swift analyzer to the detector. In this case, we are looking at mass to charge ratio, and we are looking at what are the peaks that we're detecting. Again, the intensity tells us how much, and then for the mass to Z, we should put it together as a puzzle to try to understand what is the original structure from which these mass fragments came from. In addition to that, we have a second detector, MS2 detector. So we can pick a precursor that of interest, let's say mass of interest, and we can direct those ions into the second detector and fragment it a bit further for really accurate identification of a molecular structure. Now let's talk about Auger. Auger is a technique that also provides elemental and chemical state information. Chemical state information is more limited and requires standards than in XPS. The power of Auger is, of course, in the lateral resolution. We can obtain spectra and images with as small as 8 nanometers. Here's an example of gallium map and aluminum map, which we are pushing the line here. We can see that we can actually detect 4 nanometer line from this sample. Phi Auger provides sensitivity and an abstracted vision that we need to analyze really difficult and challenging microstructure that is not possible by other instrumentation. So how does it work? So here we have electron source. So we have electron ins and electrons out. These electrons are ejecting electrons from the orbital. First we have the first ejection, and then we have an Auger electron that is being ejected. And this is what we're analyzing. So Auger electrons are counted similarly. How much is intensity of the peak is tells us how much is present, and the energy of the electrons tells what element is present on the surface. And with references and standards, we can also get some chemical information. Due to unique design of our instrument, we have cylindrical mirror analyzer. The line of sight is unobstructed of electrons. So they come out from all of the directions and directed to the detector. So we can really analyze very challenging three-dimensional high aspect ratios without any shadowing. So application of surface analysis, where is it being applied? It's everywhere. It's in energy, fuel cell batteries, catalysis, in failure analysis, in environmental remediation, semiconductor applications for microelectronics, thin films, metallurgy, nanomaterials. And this is only a subset. And today in this seminar, I will focus on 3 different areas and trying to highlight how scientists who are owning our instrument, how are they using the instrument to solve real problems that they are facing in material design, in research and development, and driving innovations. So when you think of when you design a material, what properties you really need to get from your material? First of all is, of course, chemistry. You're interested in composition and chemical structure, whether there are any impurities on the surface. If you are creating dopants, what is the distribution and what is the concentration, whether there are any surface defects that are present. And all three instruments, so all three techniques are able to provide that information. In addition, we have some options on Auger, for example, that adds additional chemical information. The second type of information is morphology. We would like to know how is all of this chemical information, where is it located? On the surface laterally and also with depths. So all three techniques will tell us the morphology, because all three techniques that Phi have is our imaging techniques de facto. So we can look at microscopic structure, at heterogeneities, and with using the ion sputterings that we use in monatomic or cluster sources, we can also look at morphology with in bulk. The third type of information that you may want to study is electronic properties, the electronic band structure, band gap calculation, work function. On our Genesis system, on XPS platform, we have additional techniques that allow us to get that information. These techniques are UPS, LIBS, and REALS. And of course, we acknowledge that when scientists and engineers, they're dealing with and designing materials, they need to be able to analyze their materials in a relevant environment. So what we offer is sampling handling solution that allow them to do that. So we have heating and cooling in situ. We have electrochemical cell that allows depolarization studies. We have inert transfer test vessels. So when you are having your design, let's say your deposition system, your synthesis system, this transfer vessel can be used to move from your deposition chamber to the analytical instrument without any exposure to the air. An instrument can also be connected to glove box directly. So there are a lot of custom solutions that we work with our customers so that they able to get all of these properties in relevant environment. So the first section that I would like to discuss, the industry application, is catalysis. So in general, how surface analysis is used in catalysis? What information we are interested in? The first is mechanism of catalysis. Surface analysis helps us identify active sites. They can find how many of those present, pinpoint their location and density, and electronic structure of active site. And that is critical feedback during the creation of your catalyst. In catalyst design and optimization, surface analysis and data are critical. They often used to be fed into models and trying to understand what are the reaction pathways, what are the binding energies of your reactant onto the active sites that you're creating. There are a lot of interfaces in catalysis: metal particles on your support, phase boundaries, core shell particles. When you engineer them, you need to really understand what is the actual surface or atomic scale structure that you created that is directly related to stability and activity. So this is how, in general, surface analysis is used in catalysis. And now I will show you several examples from papers that are published by our customers. So the first one is analysis of catalysts for water electrolysis. The analytical problem that scientists were trying to address here was trying to link the performance and what's happening during the actual test, during electrolysis, at the surface of the catalyst and ionomer. So what we see here is a high-resolution nickel-2p spectrum. And this is a great example highlighting how powerful chemical information that you can obtain from XPS spectra. So we have two different catalysts here that scientists have synthesized, and they analyze the chemistry before test and after test. And you can see that there's a curve fit results that are used to try to understand the changes in chemical composition. So if you trace the changes in the first catalyst, from pre-test to post-test, you can see that there's a rearrangement that is occurring from during testing that is indicating slight degradation. While for the second example, there's almost no changes that are happening from the pre-test to post-test. The chemistry of the distribution of peaks that you see here on the screen is very similar to before and after. So it indicates that this catalyst is much more stable. So in summary, XPS provided mechanistic insights by tracking oxidation state of the catalyst and composition. And I'm not showing here, but the authors also included study of the ionomer that is a part of your electrode layer before and after electrolysis. The second example is trying to understand whether the synthesis that is being used to create single atom catalyst is actually working. It's very challenging to create single atom catalyst that are supported on different types of supports without them agglomerating. So authors use multiple methods, but I'm showing results just from one. So they use here platinum supported on carbon-nitrogen rich matrix to create a really individual platinum atoms. So the first is we can look at surface spectrum. Surface spectrum tells everything that is present. So we can see platinum is present indeed in a high loading. And we have oxygen and nitrogen carbon as we expected from the substrate, from the support. If we really would like to analyze whether there is a metallic clustering or coordination of individual atoms, we need to look at the high energy resolution spectrum. Platinum 4F spectrum is shown on this graph. And if we look at the binding energy, it's shifted to the higher value than it would be if we would have just metallic clusters. So XPS in this case confirms that there is a chemical state evidence that metal is not being clustered. It remains as isolated atoms that is coordinated to nitrogen. So thereby, authors were able to validate this synthetic strategy that addressing this challenge of high loading single atom catalyst without aggregation. Now let's look at our application. So in this example, we were looking at silver supported catalyst on aluminum and also trying to understand what is happening, why there is a failure of the catalyst after aging, after running the test. So Auger comes with amazing images, obviously. So we have here a SEM image of fresh catalyst and age catalyst, and we have 3 Auger maps: silver map, aluminum map, and cesium maps. So silver is our catalyst supported on the aluminum, and cesium is often used to increase selectivity. So we can see that initially we have lots of small particles that are also seen in the SEM images, and after testing, these particles grow significantly in size, almost to 1 micron. So silver is being agglomerated. Support doesn't seem to show a lot of change. It stays pretty similar in terms of the size distribution. And cesium distribution is pretty similar, but they seem to be increased in concentration. So Auger confirmed with high certainty that silver particles are agglomerated, and that was causing loss of performance in this catalyst. The second technological area that I would like to show examples are semiconductors. This is definitely a very important area. Recently, there was a lot of funding and development in semiconductors, and this puts creative emphasis on surface analysis. So how engineers and developers are using surface analysis in semiconductor industry? So the first one is defect reduction and surface passivation. Passivated layers are really what reduces the trap density, and that would cause an increase in quantum efficiency and lower defects rates in devices such as, for example, image sensors. So of course, for surface analysis, we can see whether the passivation layer are homogeneous, what are the thickness of them, and relate that to the performance. The interface optimization. Semiconductor devices have many components to them. So the surface treatments that can be done to individual layers are done to improve adhesion. So XPS helps understand that and optimize those treatments, and therefore it allows to enhance reliability and durability of those devices. Engineering of enhanced output. Modifying surface properties really affects device output. So structure to property relationship, where you use surface analysis to understand what is the final structure that you made by modifying surface properties and how it directly results in your performance of the device, is one of the most common ways the surface analysis is used. And film quality it's not the only four application, but these are the main four. With high quality films on challenging substrates are very important in semiconductors. So surface analysis enables adjustment of the process of what is the solution, what is the processing steps. So really that is what's driving development of high performance transistors, for example. So let me show several examples. So in the first example, we have combination of XPS and HUXPS for HEMT device. So the analytical challenge was to analyze aluminum gallium nitride on top of gallium nitride. And the challenge analytically is to be able to use XPS for this task. If you look at a survey from gallium nitride obtained using aluminum X-ray source, you can see it in blue, gallium Auger features is present right on top where the nitrogen peak is. So if you need to quantify nitrogen or just even confirm whether it's present, you don't have any other peaks from nitrogen in your survey spectrum. However, when you use higher energy X-ray source, we can shift that feature out of the region where nitrogen peak is located, and now we have really nice nitrogen peak, and now we can quantify and confirm that we have created the expected structure. Moreover, with high energy X-ray source, we can detect deeper. So here we are trying to see how thick that top gate oxide layer actually can be, but we can still detect the underlying gallium nitride layer. And the green line is from 30 nanometers. If you normalize the spectrum, you can actually still see quite clearly peak from gallium to P. And the third type of application that you can do is we have a structure modeling software, which is Stratify, that allows us to calculate the thicknesses of layers that were deposited. So this accurate structure estimation is really critical to confirm that during deposition process, during growth process, that the thicknesses as expected were created. This next example is showing trying to attempt to characterize ultra-thin films of silver in the memristive device that does not need any electroforming. Electroforming is really important step. It's a single step that is usually applied to memristors to create conductive filaments. So it's a process that creates these conductive filaments that creates initial resistance. But in this case, engineers created a material that did not need that step. So they're trying to study what is that, why is that happening? So the silver electrode is deposited on the top of this GST, which is germanium selenide telluride layer. And what scientists have done with XPS, they followed from the top of the electrode down to the inside of the GST layer. They follow the silver 3D spectrum. And we can see that there is a small shift from top of the silver electrode, which is metallic, to within the GST layer. And this chemical shift is due to bond formation. So there are nanophases of silver with selenide and telluride that are being formed due to the dispersive diffusivity of silver. So this high diffusivity of silver creates this distributed electronic traps that eliminates that forming step. So we already have those conducting pathways for highly reproducible switching. In addition to that, scientists have done Auger, and they used actually depth profiling. So you can see here the depth profile. So we have atomic concentration as a function of the sputtering time. So we start at the top, going through the top silver electrode, and go following the silver through the GST layer. And you can see that silver is homogeneously, uniformly dispersed through the chalcedonide film. So that shows us that Auger provides additional evidence that silver was diffused in the GST layer and they're forming this basis for this forming free, uniform, reliable switching in the memory store. Now, let's see what TOF-SIMS can do for semiconductors. Of course, with TOF-SIMS having the highest detection limits, it's really great for analyzing dopants and impurities. So this example shows how we can use TOF-SIMS to evaluate impurity concentration. The challenge in this analysis was trying to quantify phosphorus isotopes in the hydrogenated silicon films that were deposited in glass. The challenge is that phosphorus overlaps with silicon isotopes. So authors had created two different calibration approaches to really derive accurate quantification. One is using silicon matrix RSF, and the second using effective RSF using simulation, a software symmetrics. So we can see that there are two samples that they've analyzed. So the first one is glass, that is as received, and these are the two curves in black and red that follow phosphorus. And you can see that it's really uniformly distributed throughout the whole device. And the second was laser annealed films that are green and blue, which is two different calibration methods again. And you can see that it shows surface segregation in the second example. So this protocol was really powerful to be able to accurately quantify phosphorus concentration in thin films where conventional SIMS would fail. The power, of course, of 3D is of SIMS is actually in mapping. So in this case, authors were trying to look at aggregates of lithium and how they behave in the perovskite cell when it's being aged in humid conditions. So here we have two different cells. One was a reference and the other is this target. And we have lithium layers, so the blue trace is the lithium that was deposited on top of the perovskite device. And they followed the lithium evolution in the perovskite device on top of tin oxide layer. So you can see that in the reference, there is a not as uniform concentration of lithium on this interface as in target device. So this lithium is really distributed much more uniformly in the target device. And they explain that by gelation of this whole transport layer, HTL, that limits, retards lithium migration. So they also used two-dimensional mapping. So they looked at lithium positive ion map at the reference and target before at the beginning and then after aging. And you can see that for the reference, we have segregation at the surface, and a target, it stays really more homogeneous. So again, they confirmed that this whole transport layer can be modified to create this gelation matrix, and that what reduces lithium salt crystallization and enhances the performance of the perovskite solar film. This example is using Auger. So in this example, it was critical to understand what is the failure mechanism of the semiconductor device that is patterned that was created by selective deposition. So when you look at the SEM images, these are node growth areas. So you should not have any growth of particles in this area. But when you look at SEM, you see that there are some particles here. The ADS map of titanium shows really homogeneous distribution. So when you look at just ADS, you're not able to understand what are those particles. While Auger analysis is with 100% certainty shows that there are 3 titanium particles that are present in node growth regions. So it highlights how important it is to look not just in the bulk, but also on the surface to really trying to understand the device failure. The last section is on batteries. So how do we use surface analysis for batteries? First is battery degradation is the biggest challenge. The stability of the batteries, there are ways to increase the stability is something that is there's a lot of effort that is going on. So the degradation of the surface and the interface is actually a major cost, and that's why surface analysis can really confirm the changes in the structure, whether it's the oxygen loss, transitions of chemicals, structure phases, and how these surface layers degradation propagates to the bulk of the electrode. During electrochemical reaction, the electrode-electrolyte interface can be broken down. So the structure of the SEI is really something that is of great focus for, and that can be tracked by surface analysis, especially imaging tools like PHI instruments offer. In order to improve the performance and stability, there's also surface coating and dopants that are being used. So if you really would like to confirm how the surface coating changes and stabilizes the surface analysis can really understand and confirm that the coating is homogeneous and how it's related to the stability of the electrode. And the same is true with additives. Additives modify SEI composition. So surface-sensitive techniques with chemical specificity can link chemistry to improve battery safety and longevity. So the first example is studying the cause of poor stability and loss of capacity in the SEI, in the silicon NMC full cell. So here we followed as a function of cycle in lithium 1s spectrum. So we can see at the beginning, at one cycle, we have an organic rich lithium fluoride stabilized SEI. But then at 100 cycles, this layer grows and it becomes dominated by organics. And this thickens and basically depletes availability of lithium, and that's what's causing degradation and failure of the full cell. The power of scanning microprobe is being able to really look at the dendrites and of the SEI breakdown formation. So here's an example of secondary electron image that is induced by the microscanning X-ray source, and we can clearly see those dendrites, and we can select areas that are small and look at what is the difference between chemistry. And a small area confirmed that there is actually lithium fluoride that is present, and it suggested that it's only present and localized at the surface because it was not detected by bulk techniques such as NMR. This is an example where an analyst trying to really understand how different ways to deposit thin films limits lithium migration for thin film batteries. And so they took created two different films. One is ALD deposition and another is CVD. And then they looked through the depth profile. So we have a lithium layer on top, followed by titanium nitride layer that is either ALD or CVD. And then we have our substrate, which is silicon. So this is just an example of how rich chemistry is and how challenging it can be. So here's the lithium 1s spectrum. But we actually have an overlap here between lithium 1s and titanium 3s. But having references, it's possible still to fit and separate out two signals. So we can see that we start with the lithium on top and go through titanium nitride layer and then completely remove it. So it's an hour of sputtering that was done. So what's happening? Why we have such different diffusion behavior of lithium? We can see that for ALD film, this titanium nitride layer, it's much thinner and it's actually less defective. It has less of oxide and oxynitride intermix layer, and that's what's blocking and minimizing lithium ion bonding and diffusion. So ALD films are much more effective barrier. Well, in CVD film, we can see that lithium diffuses much deeper, and you can see how much thicker the CVD layer is, and there is a lot of more structural inhomogeneities in this layer. The second example is combination of both OGXPS and Auger to try to understand intercalation during charge and discharge for the battery on the graphite cathode. So these are we're following intercalation of chloroaluminate ions. So we have a charge cathodes and discharge cathode, and we have Auger maps. So we have carbon aluminum and chlorine map for the charged cathode, and the same for discharged. So which clearly shows how effective the intercalation is. We have really significant loss of aluminum and chlorine. It's really decreased in intensity, while carbon, which is our graphite cathode, stays the same. So this, and we can also select and do small area analysis quantification to confirm that. While for XPS, they looked at its carbon is, again, charged and discharged. We can look at the pristine graphite and charged and discharged, so it's fully reversible. While for aluminum and chlorine, there is partial intercalation. So we can see that fully discharged is not coming back to the fully charged. It has a little bit of difference between charged and discharged state. But still, by combining these techniques, they demonstrated fast reversible intercalation process, and that what really underpins the battery kinetics and cyclability of the battery. Here's an example of TOF-SIMS, how TOF-SIMS can be used to really look at the chemical makeup and spatial distribution and thickness of the SEI layer that is related directly to the capacity fade and stability of the battery. So the authors in this paper, they looked depth profiling, and the power of TOF-SIMS is you can do three-dimensional depth profiling. So at each cycle of depth profile, you can create a map. So you can get this really nice three-dimensional volumes representative of your structure. So there's three temperatures that these batteries were tested, and let's look at the evolution of chemistry as a function of depth. So we can see that at the highest temperature, titanium has a smaller concentration, while we have much higher concentration of lithium fluoride, organic component, and phosphate. So and looking at the two-dimensional distribution, we can see that we have a thick SEI formation at high temperature, which correlates directly with increase in impedance and capacity fade at highest temperatures. So this thicker and this stratification that is confirmed by TOF-SIMS is something that is really clearly visualized by TOF-SIMS and pinpoints what is the reason of lower performance of the battery at higher temperatures. So I hope that I was able to demonstrate you several examples that demonstrate the power of surface analysis in extracting chemical information, morphological information. And I did not have time to cover some of the electronic structures, but many of these studies are also using these capabilities of using transfer vessel. I would like to pinpoint you to a paper that recently came out in the GVST in the series of guides that is focused for reducibility and improvement of quality of XPS paper published. So this paper is selecting the best surface analysis method for your material and sample. It's really great review depending on what exactly you looking with its elemental, morphological thicknesses, etc. And then what are the actual properties, energy, biological interaction, optical properties. It really helps selecting what is the most important technique. And you can see that from all of the techniques, if you look at what's the most common, XPS from the surface, XPS is number one. So this is in all Web of Science journals. You can see that XPS is one of the most common techniques, and Auger and SIMS are less popular and less accessible. And then the select surface journals have characterization method of the XPS is a number one most commonly used method.